Now let us carefully understand the problem. A solid sphere is rolling on a horizontal table without slipping. That means the translational speed and rotational speed are perfectly related. So initially the sphere is in pure rolling motion. Now the sphere moves forward and hits the raised edge head on, exactly as shown in the figure. The height of this edge is h and the radius of the sphere is r. And notice one very important thing here. The collision between the sphere and the edge is perfectly elastic. So during the collision, no kinetic energy is lost at the point of impact. That condition is going to play a major role later in the solution. Another important information is that the coefficient of friction is same everywhere, both on the horizontal table and also at the raised edge. And that coefficient is given as mu. Now we have to find two things. First, the minimum possible value of h by r. In other words, what should be the minimum relative height of the edge compared to the radius of the sphere? And second, we have to find the minimum value of the coefficient of friction mu. But both of these conditions must satisfy one important requirement. During the collision, the sphere should not slip. And this no slipping during collision part is actually the heart of the entire problem, because during impact, huge impulsive forces act for a very small time interval, and if friction is not sufficient, the contact point will start sliding immediately. So throughout this solution, our entire focus will be on maintaining the no slip condition even during this violent collision process. And this is exactly what makes this problem highly interesting. Alright, now let us begin the actual solution. First, we'll look at the condition of the sphere before the collision takes place. Initially, the sphere is rolling on the horizontal surface without slipping. And whenever a body rolls without slipping, translational motion and rotational motion are connected through a very important relation, that is v is equal to omega into r. Here v is the speed of the center of the sphere, omega is the angular speed, and r is the radius of the sphere. So this equation represents the pure rolling condition before impact. Physically, it means the point of contact with the ground is instantaneously at rest relative to the surface, and therefore there is no slipping. Now, since the body is a solid sphere, its moment of inertia about the center is I is equal to 2 upon 5 into m into r square, where m is the mass of the sphere. We will use this expression later in the collision analysis while applying rotational dynamics and impulse relations. So before the collision starts, these are the two important relations that we must keep ready. The rolling condition v is equal to omega r and the moment of inertia, that is I is equal to 2 upon 5 into mr square. Now let us move to the next important part of the solution, the geometry of the contact point. When the sphere touches the raised edge, the contact does not happen at the center level. Instead, the collision takes place at some point on the surface of the sphere. So let us join the center of the sphere to the point of contact with the rim, and let this line makes an angle phi with the horizontal. This angle phi is going to become extremely important because later almost the entire collision analysis will depend on it. Now from the geometry of the figure, we can directly relate the height h and the radius r. If you carefully look at the vertical distance, the center of the sphere is at a height r from the ground, while the edge has height h. So the vertical difference becomes h minus r, and this vertical component corresponds to the vertical projection of the radius. Therefore, sine phi is equal to h minus r upon r, or equivalently we can write sine phi is equal to h by r minus 1. And now rearranging this expression, we get h by r is equal to 1 plus sine phi. This relation is extremely useful because finally we have to find the minimum value of h by r. So instead of directly working with h, now our problem will reduce to finding the appropriate value of sine phi. Now let us understand what happens during the actual collision. The collision time is extremely small. So during this small interval, the sphere simultaneously remains in contact with two different points. One contact is with the horizontal table at point A, and the second contact is with the raised rim at point B. So impulsive contact forces will act at both points together. At point A, we have N1 as the normal reaction and F1 as the frictional force. Similarly, at point B, N2 is the normal reaction and F2 is the friction force. And these impulsive normal and frictional forces are the actual forces that will control whether the sphere slips or does not slip during the collision. Now comes a very important part of the solution, deciding the direction of friction forces during the collision. And this is the place where many students get confused. So instead of memorizing directions blindly, let us think physically. First, let us look at point B, the contact point with raised rim. During the collision, the surface of the ball at point B tends to move downward and toward the right relative to the rim, and friction always opposes relative slipping tendency. So if the surface tends to slip downward and rightward, then friction must act in the opposite direction. Therefore, the friction force acts upward and toward the left. Now this friction force is not only opposing slipping, it also produces a torque on the sphere. And if you carefully check the rotational effect of, you will see that it produces a clockwise torque on the ball. Now let us move to point A, the contact point with the horizontal table. At, at point A, during the collision, the bottom point of the sphere tends to slip toward the left relative to the table. Again, friction opposes slipping tendency. So, to oppose this leftward slipping, the friction force must act toward the right. And this friction force also produces a clockwise torque on the sphere. So, this is a very important observation. Both friction forces produce torque in the same rotational sense, and that common rotational sense is clockwise. This common torque direction will become very important later when we apply rotational impulse equation. Now we come to the most important mathematical part of the solution, the impulse equations during the collision. Since the collision time denoted by tau is extremely small, very large forces act only for a very short interval. So instead of using ordinary force equations, we use the impulse momentum principle. That is, impulse is equal to the change in momentum. Now let us first write the vertical impulse relation. If we carefully observe the forces, the upward impulsive contribution comes from the vertical component of N2. So the upward impulse becomes N2 sine phi into tau. Now the downward impulses come from two forces. One is N1 and the second is the vertical component of friction F2. Therefore, the total downward impulse is N1 plus F2 cos phi into tau. Now, during the collision, there is no net change in the vertical momentum of the sphere. So, upward impulse must balance downward impulse, and hence N2 sin phi into tau is equal to N1 plus F2 cos phi into tau. And after cancelling tau, we get N1 is equal to N2 sin phi minus F2 cos phi. Now let us move to the horizontal impulse relation. Since the collision is perfectly elastic, the horizontal velocity reverses direction after impact. And according to the sign convention used here, initially the horizontal momentum is minus mv and after the collision it becomes plus mv. Therefore, the change in horizontal momentum becomes plus mv minus mv, and this is equal to 2mv. That is why the net horizontal impulse is equal to 2mv. Now let us identify all the horizontal impulsive forces. The horizontal component of N2 is N2 cos phi, and the horizontal component of F2 is F2 sin phi, and F1 acts in the opposite horizontal direction, so it appears with a minus sign. Therefore, the horizontal impulse balance becomes N2 cos phi plus F2 sin phi minus F1 into tau, and this is equal to 2mv, or N2 cos phi plus F2 sin phi minus F1 is equal to 2mv upon tau. So now we have obtained two important impulse equations, one from vertical momentum balance and the other from horizontal momentum change during the elastic collision. Now let us write the rotational impulse relation. During the collision, friction forces act at both contact points and both of them produce torque about the center of the sphere. Since the collision takes place in a very short time interval, we use the angular impulse approach. So we apply angular impulse is equal to change in angular momentum. Now the total torque producing friction force is F1 plus F2, and each force acts at a perpendicular distance r from the center. Therefore, the total angular impulse becomes F1 plus F2 into r into tau. Now let us think about the change in angular momentum. Before collision, the sphere is rotating in one direction, but after collision, the rotational motion reverses. So the angular momentum changes from one direction to the opposite direction. That is why the magnitude of change in angular momentum becomes 2I omega. Therefore, the rotational impulse equation becomes F1 plus F2 into r into tau is equal to 2 into I into omega. Now we substitute the moment of inertia of the solid sphere, that is I is equal to 2 upon 5 into mr square, and from rolling condition omega is equal to v upon r. So the equation becomes F1 plus F2 into r into tau is equal to 2 into 2 upon 5 into mr square into v upon r, and after simplifying we get F1 plus F2 into tau is equal to 4 upon 5 into m into v, that is mv upon tau is equal to 5 upon 4 into F1 plus F2. Now we substitute this into the horizontal impulse equation which is obtained earlier. So we get N2 cos phi plus F2 sin phi minus F1 is equal to 5 upon 2 into F1 plus F2. Next, multiplying the entire equation by 2, we get 2 into N2 cos phi plus 2 into F2 sin phi minus 2 into F1 is equal to 5 into F1 plus 5 into F2. And after rearranging all the terms carefully, we finally obtain 2 into N2 cos phi is equal to 7 F1 plus 5 minus 2 sin phi into F2. And let us call this equation 1. Now we come to the no slip condition, which is actually the final and the most important part of the solution. Since the sphere should not slip during the collision, the friction forces at both contact points must remain within their limiting values. So we write F1 is less than or equal to mu into N1 and F2 is less than or equal to mu into N2. Now earlier from the vertical impulse relation we have already obtained N1 is equal to N2 sin phi minus F2 cos phi. Next we focus on the condition for minimum possible value of mu, and at the limiting condition for minimum friction coefficient, the friction at point B reaches its maximum possible value. So we take F2 is equal to mu into N2. Now substituting this into the previous relation for N1, we get N1 is equal to N2 into sine phi minus mu into cos phi. Now comes the key physical idea. For the minimum possible value of mu, the table contact is just about to lose the need for frictional support. That means this becomes the limiting case. So we take sine phi minus mu cos phi is equal to 0. And from here we immediately get mu is equal to tan phi. Also, in this limiting case, the normal reaction at the table contact becomes 0. That is N1 is equal to 0. And once N1 becomes 0, the friction force at that point must also become 0. So F1 is equal to 0. Because friction cannot exist without normal reaction. So this limiting condition greatly simplifies the problem, and now we are very close to finding the final answer. Now let us apply the limiting no-slip condition to equation 1. That is 2n2 cos phi is equal to 7f1 plus phi minus 2 sin phi into f2. Now in the limiting case for minimum friction coefficient, we already know the two very important things. First, f1 is equal to 0 and f2 is equal to mu into n2. Now we substitute both of these conditions into equation 1. So the equation becomes 2n2 cos phi is equal to phi minus 2 sin phi into mu into n2. Next, we divide the entire equation by n2. So we get 2 cos phi is equal to mu into phi minus 2 sin phi. Now rearranging all the terms on one side, we get 2 into cos phi plus 2 into mu into sin phi minus 5 mu is equal to 0. And this is the very important relation that we'll use to find the minimum values required in the problem. Now let us finally find the minimum value of h upon r. Earlier we have already obtained the condition for minimum possible value of friction coefficient, that is mu is equal to tan phi. And from the previous step we also had the relation 2 cos phi plus 2 into mu into sin phi minus 5 mu is equal to 0. Now we simply substitute mu is equal to tan phi into that equation, and we get 2 cos phi plus 2 into sin phi into tan phi minus 5 tan phi is equal to 0. If we use the identity tan phi is equal to sin phi upon cos phi, and to simplify the equation, we multiply the entire equation by cos phi, and we obtain 2 cos square phi plus 2 sin square phi minus 5 sin phi is equal to 0. And if we use the standard identity, that is sin square phi plus cos square phi is equal to 1. So the equation becomes 2 minus 5 into sin phi is equal to 0, and from this sin phi is equal to 2 by 5. Now remember the geometric relation obtained earlier, that is h by r is equal to 1 plus sin phi, and substituting the value of sin phi in it, we get h by r is equal to 1 plus 2 by 5 is equal to 7 by 5. Therefore the minimum possible value becomes h by r minimum is equal to 7 by 5, and this is our first final answer. Now let us find the minimum value of the coefficient of friction. As we have already deduced that the minimum value of mu is equal to tan phi, and the minimum value of sin phi is equal to 2 upon 5, and from it we get cos phi is equal to root over 1 minus sin square phi, and this is equal to root under 21 upon 5. As we know that mu minimum is equal to tan phi, and this is equal to sin phi upon cos phi, and finally putting the value of sin phi and cos phi in it, we get 2 upon root over 21. So after simplifying it, we get the approximate value of mu minimum is equal to 0.44. This is our final answer too. So both of the final answers are h upon r minimum is equal to 7 upon 5 and mu minimum is equal to 0.44. So the beautiful thing about this problem is that although the collision looks extremely complicated at first, the entire solution ultimately depends on combining three ideas very carefully. First is rolling without slipping, and second, impulse momentum analysis during collision, and third and the last is the limiting condition of friction. And the most interesting part is that the minimum condition occurs exactly at the borderline case where the lower contact practically loses the need for frictional support. That single physical insight simplifies the entire mathematics. Thank you.